pursued by von Mises and Weissenbach, of course. Then there is the logical.
It has nothing to do with the Venn diagram.
Same man.
Same man, but nothing to do with because I always remember by my Bayesian formula through the Venn diagram.
That's right. The Venn diagrams, Venn had contributions to, he was an opponent of subjective probability, strong opponent.
Yes.
Venn was. And Venn essentially was followed by von Mises and by Reichenbach and many others. Then there is, of course, this connection, and then there is the subjective or personalistic connection. This personalistic connection was made explicit by De Morgan. And for those of you who don't know, De Morgan was either born in Pondicherry or in Madura. So the subjective view has its roots right here.
Same De Morgan logic.
That's exactly the same man. Now, he was born, they say, in South India, either in Pondicherry, but he was English. He was not, he had a French.
How do you know? He probably took an English name.
No, he was a Huguenot, like de Moivre.
Oh, I see.
De Moivre really invented the central limit theorem, not Gauss. That's another misnomer. And then,
Madurai, according to Wikipedia.
sorry?
Madurai, according to Wikipedia.
Yes, but by the way, there is also a book written by Sam Cox and some other people, and I think they mention Pondicherry. So we just don't know, but it's in this region. Okay, thank you. So the frequency interpretation of probability is the limit of a relative frequency, and it's unique. The extreme alternative is the necessarist view, and the necessarist view is by Carnap, Keynes, and others. And I'll try to pursue
No,
this.
what is unique? The probability?
The probability has to be unique.
That is so in all of...
No, not in the subjective setup. In the frequentist setup, if you can indefinitely repeat an experiment, and I'm going to criticize that. Whatever experiment, probability of head of a coin.
But that's a simple one, but there are several cases in which it's very hard to
Well,
decide what-
this is where the big issue comes, that there are many cases where you can't repeat this issue, and if you ask what's the probability there'll be a World War III, you cannot keep having World War IIIs over and over again.
Or the famous thing, what's the probability that the man has two boys?
Okay, that may be another one, or the other famous question is, did Shakespeare write Hamlet? Or things like that. So, the necessarist view is a little different, and it's due to Keynes. I won't pursue this for shortness of time. What happened? Okay. I won't pursue this Keynes's view for the shortness of time. But I will comment a little bit on I'll comment a little bit on the empirical view. And let me see, where are we? Oh, before I go there, there are two other notions. One is intuitive probability and one is propensity. The intuitive thesis in probability holds that probability derives directly from intuition and is prior to objective experience, namely data. It holds that experience is to be interpreted in terms of probability and not probability to be interpreted in terms of experience. Completely opposite of what you all do as statisticians and data analysts. Completely different perspective. Okay? Intuitive probability can be seen as belonging to both the logical and the subjective connection. And subjective because the axioms of intuitive probability, they are not really due to Kolmogorov, they are due to Bernstein. Kolmogorov formalized them and definitely improvised upon them. And they are logical because the development of an additive probability measure is based on arguments of logic due to Keynes, Jeffreys, and Cox. And since I give this talk to people who are not physicists, I emphasize that physicists have contributed to this, in all fairness to what they have done. So Jeffreys and Cox were physicists. Keynes was really a probabilist, but went into economics eventually.
I think Keynes had some physics background, if I remember.
He may have had physics background. And Bernstein was the first to suggest the axiomatization of probability. But I think the idea of axiomatizing probability goes back to Borel, and I'll come to that.
In their problem semantics, I mean, what is axioms?
Oh, no, we can go into that, what we mean by an axiom. An axiom is supposed to be an unquestioned belief, assumption, or truth. That is an axiom. Like, nobody likes to go to a gambling house and lose money. You know, it's an axiom. Of course, somebody may say that I like to go to the gambling house because I get pleasure out of gambling. Even if I lose money, I have a utility in getting pleasure. But let me just cite this quote by Kolmogorov. I've done it before. Let me come back to it later on. What's happening? And so here we have the propensity notion that I mentioned. And basically the propensity notion is the one I'm quite attracted to. It says that probability is a disposition or a tendency of a given type of physical situation to yield an outcome of a certain kind, or to yield a long-run relative frequency of such outcomes. I find this attractive, and I want to say a little bit more about what's going to happen. Popper claimed that propensities or chances are unobservable dispositional properties of the physical world compared to a Newtonian force. All right. And Kolmogorov talked about propensities without using that word. He used the word generating conditions of an outcome. And therefore, in some sense, both Kolmogorov, Di, and many others, Cox and others, they were all contributing to the notion that probability is not a relative frequency. Somebody said it's a very intuitive basic thing. Somebody said it's a logical connection, and if you don't follow the logic, I believe that is the Cox's argument, you will be incoherent, and so on and so forth.
So if you think of it like this, then things like did Shakespeare write Hamlet?
Yeah.
You cannot assign a probability to that because it doesn't make any sense to talk about a propensity for this. Right?
It doesn't make any sense to talk about a propensity for this, but I want to come to that in a second because there is a very famous theorem which all of you who call yourselves Bayesian should know. It's known as Di theorem. Are you familiar with it? Well, Di did something brilliant. He connected the objective and the subjective view of probability through his theorem on exchangeability. Therefore, exchangeability is very fundamental, and I want to talk about it. And here is the simple illustration. Suppose I'm tossing a coin, and I want to know what's the probability that it will be heads on the next toss. And the way I think about it is I assume that if I were to toss the coin an infinite number of times, it would have a tendency to fall heads so many proportion of times. If I were to know that particular proportion or that propensity, I could answer your question. But because I don't know it, I'm going to assign a prior distribution to it. And my bet on the next outcome will be a consequence of averaging that propensity. That is essentially the theorem of definity. I'll try and highlight it a little bit. So here it is. Comments on the frequency theory. So let's just talk about this objective frequency theory which von Mises and which what's his name?
Fisher?
Who?
Fisher?
Fisher, no. Fisher was not clear about it. Fisher was a bit confused. Fisher was a very practical man, very creative man, did a lot of things, but never went into the guts of the issue. Yeah. But Fisher did not contribute to the subjective theory. So there were many people who were opposed to the subjective theory, but they didn't really offer an alternative. The closest that I think were Popper and Kolmogorov. But Popper went astray. He thought that propensity is a substitute for probability. And he failed miserably because the conditional probability argument could not be justified for propensity. Therefore, propensity as such itself is fine, but it doesn't replace probability. Okay, so let's look at the frequency theory. Consider the statement, the probability that a particular coin will fall heads when tossed is half. We all get that. According to the frequency interpretation, the following is the most common. Look at these words. If the coin is tossed a large number of times under similar conditions, it will fall heads in approximately half the tosses. All the red underlined words are caveats. How large is large? What do you mean by similar? And what do you mean by approximately a half? Now that is the definition of the propensity theory, the frequency theory. So this interpret has too many. Sorry?
In the last slide,
Yeah.
the last slide, you said a particular coin.
Yeah.
I think the better or more consistent word should have been a fair coin. Because
Oh.
putting number half.
Yeah, but it doesn't have to be fair. It could be an unfair coin. The probability of head will not be half. It could be something
But
else.
then the assumption.
Yeah. Well, we made an assumption of a fair coin, which means that it will land. But the coin could be loaded 3/4. And if I wanted to know, if the coin was used in a gambling house, it's not going to be half. It's going to be loaded. Okay. And you want to know what's the probability of head. Let's say you want to know. And it says keep tossing this coin an indefinite number of times. So how large is large? The notion of infinity is metaphysical, even though in Chennai we have to be careful because the man of infinities was here. Ramanuja was here in this area, right? So anyway, what does a similar coin mean? If the same conditions hold, then you'll get the same outcome. How different from same is similar? How close to half does the term approximately mean? Notwithstanding the above, this interpretation applies only to conceptually repeatable experiments like coin tosses or light bulbs. Indeed, von Mises, the strongest advocate of relative frequency theory, claims the only aim of such a theory of probability is to give a description of certain observable phenomena, the so-called mass phenomena, and repetitive. So von Mises, when he was pushed heavily, he didn't invent the notion of relative frequency, but he was an advocate, a strong advocate. He had a physics background, and he was thinking like a physicist all the time. And he was challenged most of the time by the other people around him at that particular time. And so he finally conceded that, well, the only way we can use this definition is for mass phenomena, like failure of light bulbs, screws, coin tosses, card games, and so on and so forth. If you ask the question, what's the probability that Shakespeare or Hamlet, he said, this is not a question to be answered by probability. Second thing, when he was pushed, how do you assign an actual number? He said, well, that's the job of a statistician. So he kind of evaded the issue many times. But he was the predominant, but here he says, but I decline positively to apply the mathematical theory to questions like what the probability that Napoleon was a historical person rather than this is cooking So von Mises refused to apply. The following striking quotes are also noteworthy. The frequency concept, based on the notion of limiting frequency, as the number of trials increases to infinity, does not contribute anything to substantiate the applicability of the results of probability to real problem. The frequency concept applied to a large but finite number of trials that does not admit a rigorous exposition within the framework of pure mathematics. And that is Kolmogorov. So Kolmogorov essentially denied relative frequency as an interpretation. And that's a quote here. Okay, where do we go? What about the physicist Jeffreys? Jeffreys and Rinch argued, among other things, that probability should be regarded as a primitive concept, not to be defined in logical terms, and in particular, not the limiting frequency definition, and the limiting frequency definition is not operational. So at least we have one thing coming out clearly, at least in my mind, that this relative frequency theory, which is associated with the objective theory, has been the subject of severe criticism. And therefore, a lot of classical statistical procedures like p-values and t-tests and maximum likelihood and asymptotic distributions and all have to be really taken with a grain of salt. So what happens next? What do we have left? Classical probability, the notion most commonly used by Bernoulli, Bayes, de Moivre and Laplace, and currently used in introductory probability tests, is based on the principle of insufficient reason. It implies the probability of a coin landing is half because there are only two possibilities, heads and tails, and they are equally likely. Thus, heads and tails should be assigned the same probability. And the maximum entropy principle is a manifestation of the above, which you heard in the lecture this morning. So that's the old view of probability, but the argument is circular, because the term likely is used to define probability and probability is used to define likely. What if the coin is unbalanced so that we cannot regard heads and tails as equally likely? And the third argument is physically impossible to produce a balanced coin. So even if you want to follow Bernoulli and Laplace and you say the coin is fair, it's a judgment. Therefore, it's personal.
It is not a judgment that the coin is fair. It is what it says. It is insufficient reason. You do not know. That is all it says.
But then you make a judgment that it's
No,
fair.
there is no judgment here. You do not know. Since you do not know, you have no reason to believe it will fall heads more often or tails more often. That is all it says.
So you're basically saying, therefore, you give them equal probability.
That is the best prediction you can make given the information you have.
Okay,
So
you can go with that.
there is nothing circular about it.
Oh, the definition is circular, because you talk about it in terms of likely.
See, you also put that it's insufficient reason. That's what it is. It is not a judgment.
No,
it's
but
insufficient reason.
insufficient reason is one of the arguments, you know. The other argument is also the argument of fairness. A fair coin is tossed. All books start with that particular premise, but no matter which premise you use, we have some issues. But even if you assume that there is insufficient reason, it's again a judgment. In my opinion, I don't have sufficient opinion, but you may have it. So we can go with that. All right, some quotes on subjective probability. We are therefore driven to the supposition that the degree of belief is a causal property which we can express vaguely as the extent to which we are prepared to act on it. The degree of probability attributed by an individual to a given event is revealed by the conditions under which he would be disposed to bet on the event. That's definitely. And the personalistic view holds that probability measures the confidence that a particular individual has in the truth of a proposition. So there was a lot of discussion about subjective probability, which was rather vocal. Can we come up with a mathematical development of subjective probability?
I think
That-
Elsevier has done that.
Sorry?
I mean, it has been done, and Professor Elsevier has done it, talked about it in 2 lectures now.
Not what I have to say. He has not given you the axioms of subjective probability.
But
He has derived, no, listen to me what he has done. He has taken the notion of probability as being fundamental, and he has developed the consequences of it. The axioms of subjective probability have not been discussed by him, and I'll flash them to you. Okay? Let me just go to the axioms. Okay, here's the De Finetti's theorem, linking objective and subjective probability. The word chance has been used in 2 contexts, propensity and the limit of a relative frequency, both viewed as being objective. De Finetti acknowledges chance as a useful entity, and his famous theorem of exchangeability talks about linking the two. Ansgar Oman got the Nobel Prize, do a similar thing, but we are the von Neumann-Morgenstern axioms of utility. In other words, the objective and the subjective notions can be combined in one of several ways. One way being De Finetti's.
In what way is propensity, as you have described it, objective?
Because it talks about the conditions of the experiment which lead to the result. It's an undefined concept. It says it's like specific gravity or mass. It's a property of the physical world. That is what propensity is.
I didn't get the definition.
I did not put it up in detail, but I have written a book too. And feel free to buy it. It's expensive. Okay. Okay, how do we characterize statistical practice? The interpretation of probability is the key driver of statistical methodology and the development of algorithms for information processing. The concept of probability, most unanimously adopted by statisticians, is frequency. Therefore, they are called frequentists. And they have produced a powerful arsenal of practical tools. Nothing wrong with the tools. It's just what's the foundation. By contrast, Bayesians are those statisticians who adopt the subjectivist concept of probability, use Bayes' theorem. And there is something which nobody in this meeting has thus far discussed, namely the likelihood principle. There is a principle which drives Bayesian practice, and it's called the likelihood principle. And the likelihood principle essentially says that your inferences should only be based on the data you observe and your prior, and not on the data you could have observed but you did not observe. The talk on the frequentist talk we heard on p-values, when you're computing a p-value, you're talking about things you have not observed. That is the basis of the p-value. How surprised are you means what else could I have observed? So the likelihood principle is another thing which drives the Bayesian argument. There is another community, it's called objective Bayesians. Currently, it's the fastest growing segment of statisticians. They employ the tools of the subjective Bayesians, but uphold the thesis that probabilities need not be subjective, nor logical, nor unique to individuals. So there is a little mixture of things going on. In doing so, they violate the requirement of coherence. That is, they put flat priors on the real line.
Maybe I'm incoherent, but I did not see any contradiction between calculating the p-value as you described it and using Bayesian methods to calculate probabilities. One can do both. I don't see why one contradicts the other.
Look, man, it takes a lot of reading before we can jump into these things. I used to be a frequentist too.
Right.
Okay, it took me a long time to understand what I was doing. I was using the methodologies. They are very different. The likelihood principle essentially says you have only one likelihood, and your posterior should be based on that likelihood.
Yes.
The frequency concept says, yes, I have observed one likelihood, but I could have observed several other likelihoods.
Yes.
Okay? And therefore, I'm just not going to look at the maximum of the likelihood. I'm also going to look at confidence intervals. I'm going to look at the consistency of the estimator. I'm going to resort to frequentist machinery. And the p-values is a function of frequentist machinery.
But it is fair, it's just a probability question to say, if I throw a fair coin 100 times, what's the probability that I get more than 70 times heads? I can calculate that probability.
You said if it's a fair coin, then why do you want to calculate the probability? You already said it's a fair coin, it's half.
No, I can calculate that number. And that's
You
a
said
number in probability theory. If now somebody wants to apply this to say something about the coin...
By the way, this is a Bayesian meeting. Why are you talking about non-Bayesian methods?
Can I put it this way? I think you are attacking the strawman Bayesians here, and the real Bayesians are not like the picture that you are portraying in these notes.
What do you mean?
Real Bayesians don't have something like a likelihood principle. People actually use Bayesian statistics.
Would you like to bet with him?
No.
The game is over. The fundamental principle of Bayesian inference is the likelihood principle. It drives the Bayesian argument.
Okay,
Bayesian inferential argument. And to say that you have not heard about it, is something.
We can define Bayesian, and that's fine. I wasn't trying to propose a frequency method. I'm just saying that one can calculate a number.
Yes.
If you have a fair coin, you can calculate the probability that you throw 70 heads or more. And that you can do. That's a simple probability calculation, some binomial.
You seem to be going round and round. You said if
I'm
you have a
not
fair
If you take
coin.
1 minute to listen to what I have to say.
Oh, I think you should be listening. to others too. I mean, if you say you have a fair coin, then why do you want to calculate the probability of head? If you don't know what is the coin,
You have let me put it this way. You have two hypotheses. The coin is fair, the coin is not fair. Yes. You are evaluating these two hypotheses. You observe, and your null hypothesis is that the coin is fair. And you observe 70 heads and 100 tosses. Right. What you calculate, how do you calculate the p-value? There is no contradiction in the Bayesian view and what was discussed earlier about this question. That is the position.
no, there is a big contradiction.
Okay, let's continue this.
Okay, well, I suggest you read it. The Bayesian approach does not use p-values. I'm not saying that p-values is not useful. It is very useful, but it is not a Bayesian approach. The p-value is essentially does not adhere to the likelihood principle. The likelihood principle demands that you base your posterior distribution only on the data that you have observed.
In the morning, Professor Sivia started from the principle of indifference and derived the probability of picking, for example, balls from urns and went to the continuum limit. All this is from a Bayesian point of view. You apply to a coin, you get exactly the same results that anybody else would get. There is no contradiction here.
What you're saying is that the Bayesian result and the non-Bayesian result could be the same.
And you can talk about the p-value in both languages.
I don't think so.
Can I make comments here?
Yeah.
I know where your confusion is. The thing is that the p-value is fine, you can calculate it. The thing is, do you use the p-value for hypothesis testing or not?
Oh, that's a different question.
Say you do not use the p-value for hypothesis testing.
That's a different question, yes.
No, but that is, I think debate is over that rather than whether the p-value is something Bayesian or not.
No, we can just mention the p-value is based on hypothetical replication of the data generating process, which is actually never done. Whereas when we take a Bayesian analysis, the only thing that is real is the small number of data that's actually collected and measured.
I think what this gentleman is saying is exactly correct. That the p-value is based on a hypothetical repetition of the experiment, and the likelihood principle says that your inference should only be based on what you have observed, not based on what you could have observed, which is the hypothetical repetition of the experiment which gives you the p-value. So a Bayesian would not use p-values. He may compute it, she may compute it, and she may use it in some informal.
If you say a p-value of less than 0.05 is a meaningless test, I'm fully with you. So if that is the point, let us proceed.
I'm not even talking about the numbers. I'm talking about the concept of the p-value. Concept of the p-value is what brought about the Bayesian movement. The modern Bayesian movement came about more because of the concept of a p-value. And a good Bayesian will not use p-value. A good frequentist will not use the posterior distribution by the same token. So, it's a two-sided. You had a question?
No, so I'm saying that if you use Bayes theorem for data analysis,
Yes.
the likelihood principle is unnecessary. It is automatically encoded in Bayes theorem itself. So I'm not invoking it separately.
Oh, you're invoking it.
I mean,
It's automatically encoded.
It's automatically encoded. So
Correct.
that's why you want to elevate it to the point of principle.
Oh, it's become no, because there are other. No. There are
Inference, statistical inference should be based on the data that's actually.
That's Bayes theorem itself. When you're inverting data and hypothesis, that's automatically there in the
But conceptually, it's not very apparent to many people unless it is
No, I mean,
stated.
that's because you're coming from a frequentist background. If you were doing strict basic things, like you
well, that's part of the reason why you are not hearing the word likelihood principle here, because we are not debating Bayesian methods versus non-Bayesian methods. If we were debating that, we would simply say that the likelihood principle is violated by the non-Bayesian. That is exactly what we would say. Now, there are other reasons why the likelihood principle plays a key role. If you want to read up on it, there is a book by Berger and Wolpert called The Likelihood Principle, and there are some very key papers which are constantly used to invoke the likelihood principle. Okay, so the likelihood principle plays a role. Well, where am I going? I'm going here, and they violate the requirement of coherence, and somebody can say, so what? I'm incoherent, but that's not the argument here. Okay, I'm going to skip this and I'm going to talk about something else. I'm going to talk about the axioms of subjective probability. Okay, the theory of subjective probability, an overview. Each person needs to assign a numerical probabilities to a subset S of the sample space to reflect beliefs. Like Euclidean geometry, subjective probability begins with a list of undefined terms and a list of postulates called axioms. These are derived only after a thorough examination of our intuitive notions on the subject. What axioms are needed to produce such probabilities from more basic qualitative relationship representing the person's judgment about which events are more likely to occur than the others? So, suppose we have two events A and B, they belong to the sample space, then there exists, this is mathematical, exists a binary relationship denoted by that wiggle such that A is preferred to B, or A is more likely to occur than B, or B is more likely to occur than A, or both. If A is more likely to occur than B, then that is what it means. What is this notion? It's an undefined primitive relationship, and we assume that the person can make the judgment of A more likely to occur than B or not based on intuition alone. That's where it begins. Oops. We say that the probability distribution P defined on the subsets of S agrees with this if A more likely than B implies the probability of A is bigger than or equal to the probability of B. And the question is, what axioms must be imposed to guarantee the existence of a unique P that agrees with it? That was the key development. And there must be some problem with my slides, but here are the axioms. These axioms were not presented by Professor Smith. These are very, very different.
They weren't presented, but they were mentioned when they mentioned Cox's.
There's a little difference between what Cox has done and what's going on here. Okay? But there is a similar pattern of thought. But remember, these things preceded Cox as well. These were almost due to Ramsey. 1930, 1931. There's another powerful idea here, which is not being completely expressed, that probabilities and utilities are bound. You cannot separate probability from utility. That's a very difficult notion to put forward.
In the prior.
Any probability assessment, yes, mostly in the prior, because once you have the prior, everything else follows. Once you have the prior and the likelihood. So there's the first axiom that says that either A is better than B, or B is better than A, or E is equivalent to B. And then there is a theorem. Axioms 1 and 2 imply transitivity, and the theorem 1 implies that the relationship yields a total ordering of the subsets. I think the second slide may be a little messed up. Here's axiom 3. That S is always more likely to occur than the null set, and any subset is more likely to occur than the null set. And then we have theorem 2, axioms 1 to 3 imply that if A is a subset of B, then B is preferable to A. Somehow these axioms parallel the Kolmogorov axioms. But the Kolmogorov simply said, take these axioms and go build a house. What Di Finati and Savage and Ramsey did is said, let me start with more basic axioms of human behavior and see how far I can go. And these axioms, the first 3 axioms, are essentially a reflection of human behavior and preferences. And they lead us to these theorems. Axiom 4 is a technical axiom. I'll skip it. I'll skip discussing it. And axioms 1 and 3 have their origins.
Wouldn't axiom 1 be deductive logic?
Yes. Is what?
Deductive logic?
Yes, it is.
Then why should it be behavior?
Well, it says that if I have 3 choices, if I prefer A to B, and if I prefer B to C, then I must prefer A to C.
No, but
that's basically.
behavior is not necessarily always logic. That's right.
Oh no, behavior is not logical, but in this case it is.
So axiom 1 does not affect behavior. It applies to preferences and view propensities, if you like.
No, it doesn't.
But I may prefer A to B, B to C, C to A in terms of.
By the way, these axioms are violated sometimes, and that is the discussion. That is a Nobel Prize. Somebody got a Nobel Prize for saying that these axioms are not necessarily followed by humans. And there is a nice example. And then Rajiv gave an example of that. Rajiv was showing an example. So,
Sorry to interrupt you, but these axioms seem to follow from the rules of inference of logic.
well, at least, I'm not sure. Okay, they may.
Transitivity, for example.
Transitivity, yes. But I'm putting these up. Okay, this is how the argument goes. But let me go further. There is another axiom. Axiom 4 is due to Villegas. That's a technical axiom. Then Di Finetti wrote this paper and said, are these axioms enough to guarantee a unique probability? The question was open for a long time. And in 1959, there was a paper by Pratt, Kraft, and Seidenberg that showed that those axioms are just not enough. We need another axiom. This is what I call the axiom of acrobatics. It says there is a random quantity with a uniform distribution on 0, 1, but not a uniform distribution in the sense that you know. It's a uniform distribution in a different sense. Let X be a random quantity taking values in 0, 1. Let I be a subinterval. And then for any two subintervals, I1 preferred to I2 means the length of I1 is bigger than the length of I2. So the measure theory ideas come here. And now we need that additional axiom. And under that additional axiom, we have the final theorem that if we were to subscribe to these axioms behavioristically, then there exists a unique probability, a unique quantity called P of A, which satisfies the Kolmogorov axioms. So these axioms precede the Kolmogorov axioms, and the P of A satisfies the Kolmogorov axioms. So the argument is a little more involved, but I'm just putting it. So, theorem 4, as defined above, P is a unique P which agrees with me, and these are, furthermore, this P satisfies the Kolmogorov axioms, and these are the Kolmogorov axioms. So what do we have? Where do we stand with all this? A couple of other things. Di Finetti's development, only finite additivity matters. Countable additivity is an expedient, even to Kolmogorov. Axioms 1 to 4 specify how we should behave. Axiom 5 prescribes how to quantify uncertainty. It is the yardstick of quantification. What's the bottom line of all this? The bottom line of all this is that we can come up mathematically with a quantity which we call P, which we have difficulty interpreting, but which behaves in a way which satisfies the Kolmogorov axioms. Kolmogorov essentially took these axioms and started working. What Savage and Di Finetti did is went behind the Kolmogorov axioms to introduce the axioms of behavior and the axiom of measurement, and proposed an interpretation of probability that was axiomatic. Now, Cox may have done similar things. I have not read Cox completely. I'm still struggling to understand Savage.
So Cox's axioms are kind of different, actually. I take back what I said. You said they're different, and Cox are different.
But similar line of reasoning, because I have tried to read Jeffries, and in Jeffries there is a...
Jeffries is older than Cox. Cox is 46 or so.
Oh yeah, Jeffries is 33.
Right. So Cox is very well summarized in James's book, which you should be able to.
I have Cox's original paper.
Yes. But it has been improved over the years.
Probably it has been improved, but then, of course, if I were to spend time, I would probably read Savage. I mean, I have to decide where I want to put my time. I'd probably read Savage because it's the more complete, it's probably a more complete. But a couple of things. There are points that Savage makes that we should really be careful. Ramsey and Savage simultaneously derive subjective probability and utility by imposing conditions on this relationship. Di Finetti derives probability through scoring rules. Di Finetti went also further and said, suppose I was to gamble with you, and if I was to be scored based on my gamble, then if I were not to lose, then the 3 Kolmogorov axioms fall. I'll close this quickly. Well, there is also another axiom which talks about conditional probability. Because remember, Kolmogorov waved his hands and called conditional probability a definition. There's another thing Kolmogorov did.
So again, if you do Cox's treatment, it has 3 what James calls desiderate or other than axioms, but they are desirable properties. And with those, you basically start with proving conditional probability. And
as I said, I have not read Cox.
Yeah.
And I should have read, knowing that I'll be surrounded by hostile physicists. Yeah, I'm done, actually. I'm done. What's the point I want to make here? The next point I want... All right. There's this famous Ellsberg paradox. Ellsberg is the same man who Pentagon Papers man. What did he show? He showed that humans don't necessarily behave according to these axioms. They violate these axioms. And he gave examples. He never got the Nobel Prize, but this is analogous to what Rajiv was putting up. And Kahneman and Tversky also came up with examples to show that people violate these axioms. And so did another French economist called Allais, came up with a paradox. He took out a Nobel Prize. 4 to 5 people in this area have got Nobel Prizes. Owen got a Nobel Prize for this work. They say if Di Finetti was alive, he would have got a Nobel Prize. Kahneman and Tversky got a Nobel Prize. Allais got a Nobel Prize. And Arrow got a Nobel Prize. The first Nobel Prize. They're all in economics. So these, and there is an open question that comes up, and this is my last slide. Does nature subscribe to the axioms of coherent behavior expected of humans? Feynman, your famous physicist. Fine. I have his paper. I tried to read it. I think he didn't quite understand probability, but he made a noble effort because he denied the addition rule. So if you were to follow Feynman, you wouldn't be a Bayesian. I mean, Bayesians wouldn't.
it's probably talking about amplitudes.
Yeah.
Whatever it is, he denies the addition rule, and I have his paper.
Yeah, well, that's probably a quantum mechanics.
Yeah.
It's not happening to find.
It's not that probabilities don't add, it's probability amplitudes don't add, and those are the objects that quantum theory deals with.
Okay, but Feynman's paper is in my room right now, and if you challenge me, I'll bring it down. He basically says that nature does not follow the laws of probability. And he comes with this double split experiment and does that. But that was long ago. But I'm saying we would all, if we were to subscribe to what Feynman said, we wouldn't be doing Bayesian statistics.
That's not.
Sorry?
That's not true, because I subscribe to everything Feynman said, but I also do Bayesian statistics.
You do Bayesian.
That's true for most of us here.
Okay, but then the addition rule is gone. That is
Addition
the law.
applies to probabilities, and these are amplitudes he's talking about, not probabilities. So these are complex numbers. So I think we need to look at it.
No, he gave a talk before a group of statisticians. The paper that I have was published in the Berkeley Symposium. Basic message was, fellows, this addition rule of probability doesn't hold for nature. That was his point.
because you add the amplitudes and then square them. You don't square the amplitudes and then add. That's his message. But
Okay.
the key object is the amplitude, not the probability.
Whatever it is.
Very well why he says that, and I also agree with that. But it's a little bit of a sort of a slide of speech to say nature doesn't follow the laws of probability. It's a sort of a little bit of sort of artistic license.
But that is what Feynman means.
I know that's what.
Okay, that's right.
Feynman like to be controversial. That's
Well, that's great. There's another, recently in the physics review, a paper has come out by a physicist from Cornell whose name escapes me, but he's very well known. And he has said that subjective probability, and I happen to have that paper with me, subjective probability can resolve some of the paradoxes of quantum theory. And there are three physicists, one of whom is already corresponding with me. They call it Cubaism. Cubaism. Have you heard of it?
Ravi might have heard of it.
That's kind of an attempt by people. So what the people involved in this are essentially Chris Fuchs
Chris Fuchs has been writing to me.
and
Merman.
Arjun Caves and Shack.
Yes, and Merman is the physicist from Cornell who has written a very nice article.
Yeah, so that's still something that's not completely settled, because even there are different views on how to really go about essentially formulating a theory of inference within quantum theory itself. I mean, essentially what you want to do is you want to separate the ontological aspects of the theory, aspects that refer to causality and things about physical reality from the subjective aspects where they were doing inference. So they want to separate these two things neatly and say that this is the theory of inference and this is what you're trying to learn about. So I'm not sure. It's kind
Well,
of
anyway, it's a recent development that seems to be.
yeah, but it's still in its infancy, I think.
Oh, of course, it's in its infancy, but there's a big movement in that direction.
Yeah, I mean,
So that's all I want to say. Well, I have nothing more to say other than.
Okay. So let's more questions.
Yeah, I'm happy to answer questions.
Yeah, questions?
Yeah.
Okay, so it's all nice to see the foundation development, but are there specific instances where your particular persuasion actually makes a difference?
Where my actual, yes,
Whether you're subject to Bayesian or
absolutely. In a court of law, if you're going as an expert witness, this question comes up quite a bit. Whether you should, how you justify your testimony. Okay. In a court of law, right, judges and courts, these kind of ideas play a role. If you ask me what my personal experience with this has been, the one problem I worked on was in particle physics, where I had a problem similar to what you were talking, where you had more parameters than equations. And how do you estimate those parameters? So I did work with a physicist, particle physicist. We developed a Bayesian approach. We came up with answers that could be justified by the independent physics, and we could go beyond, and it's published in the statistics literature.
Sir, is there a Bayesian alternative to hypothesis testing?
Yes. There is a
Bayesian hypothesis testing.
Or is that?
There is a Bayesian, you compute base factors, you compute the prior odds and the posterior odds, and in fact Jeffries has contributed to that.
There's an entire chapter in James's book on that.
But why people not following it?
People ask. Ecology is usually
Computational biology and many other hypotheses.
No, people are following it. I think your weather models community follows it. I have no idea which community you work in, but the community I work in, Bayesian hypothesis testing.
I work in machine learning.
In what?
Machine learning. And computational biology, they follow the other one.
Okay, very good.
All right, if there are no questions, quick announcement. Tomorrow, the first talk will be by Eric Van Hemingen, and he's going to give talks with Brazil. Tomorrow we start at 9. Tomorrow we start at 9.
And if you haven't written your working differences, please also.
First talk is not by you.
First talk is by you.